All right. Now, we talked about, is that me or no? That's me, okay, sorry. All right, so we talked about binders this morning. We talked about aggregates in the afternoon. So we looked at individual properties. We selected the aggregates. Now we get into asphalt mixture volumetrics. Now, the Superpave system, we talked about again, binders. Oops. Okay. Go back first. Okay, perfect. So, so we talked about characteristics of binders, how they affect the performance, Superpave binder tests and parameters, Superpave binder performance grading, we talked about it, and then aggregate properties. So, in essence, we have been looking at individual components of an hot mix asphalt. So, we looked at binder, that's the fluid. We looked at the aggregate, that's the stones. Now, we are putting them together. And how we put them together is extremely important. So now we're going to look at the Superpave mixture design. Superpave mixture design is based on volumetric properties. Now, there is a big debate going on right now within the academic community of asphalt mixtures. If you go to Transportation Research Board, there is a debate going on right now. The debate is like this. So there's a group of people who says, well, we shouldn't be specifying volumetric mix design. We shouldn't be specifying how much binder to put, how much aggregate to put. What we should be doing is, well, we want the performance property A, like dynamic modulus we talked about. So we want the dynamic modulus, just like we have the dynamic shear modulus for the binders, there's a limit, right? G star needs to be larger than 1 kilopascals at T high. So we have a specified property for binders. Why don't we do the same thing for the mixtures? So let's just specify, no matter what you put in that mixture, we want an E star, which is the dynamic modulus of the mixture itself, should be greater than this. And maybe other properties like, there are many other mixture tests out there. There is the semicircular bending beam test. There is the push-pull fatigue, beam fatigue. So let's just specify mixture properties and then how that works. Well, and the other side, the debate, other side, no, we still need to be specifying volumetrics. It needs to be based on volumetrics. Currently, what we are trying to do with the mixture volumetric design is we are trying to achieve a performance level on the mixture level by specifying the volumetric properties of the different components. Aggregate amount, void amount, how much of the voids are filled with asphalt. We are trying to come up with some kind of a recipe such that we will have an acceptable performance. So in this debate there are advantages and disadvantages to both. Obviously, volumetric mix design is extremely easy in terms of, you don't need a device to test. The dynamic modulus testing, you even need the actual servo-hydraulic device to run the test. Nowadays, the test device doesn't cost much, but still, it is out there. Now, but current specification, everything is based on volumetrics. So we come up with a whole bunch of criteria for the mixture to work well, properly, in terms of rutting and fatigue cracking. So that's what we do. We do a lot of analysis, density void analysis, and we find optimum asphalt content of the binder based on certain criteria, such as voids in mineral aggregate, VMA, such as VFA, voids in filled with asphalt. All these properties are targeted towards a certain acceptable performance. That's what we're going to talk about today. Now, let's look at the future first. So this is one of the slides that I'll be showing. It shows like slide 38 here. This is what we're going to do at some point. So for example, in this example, we're going to solve is a hot mix asphalt surface course. We have a surface course of 38 millimeters thick, 1.5 inches, to be designed to carry 15 million easels. During the life of the pavement, in a location, 15 million easels during the life of the pavement, at a location where the average air temperature is 41 degrees Celsius and a 9.5 millimeter nominal end mass is required. This is the nominal maximum aggregate size. And we have 4 different aggregate stockpiles that we can use. And based on the environmental information, we already did the phase 4 this morning study. We know what binder to use. So this PG 6422 binder to use. So we have this binder. Now, what we need to do is we need to come up with a job mix formula. How to come up with a job mix formula or come up with a design aggregate blend and asphalt content. How many of you have done a job mix formula, done a Superpave mix design in the past? Of course, nobody, because why would you be here then? Right? This workshop wouldn't be appealing to you. Of course, and I was first worried about at least one end, but it's good. Good. So that's why you're here, to learn, so that what people, the technicians who are working for you, what they do. That's important. If you know what they do, you don't necessarily do them, but you know exactly what to look for and what not to look for. And if you see a problem with the job mix formula, you will be able to identify it in no time. So let's do this. Now, aggregate blending is the very first step. Now, so we have different sieve sizes. We know all this. So different sieve sizes, different, number 4 sieve, number 200 sieve, and these are the sieve sizes. One thing that's important is that in Superpave mix design, we use a 0.45 power chart. So we don't directly plot the gradation and the horizontal axis as your size, the vertical axis on your percent passing. We don't do that. We actually have a specific chart called sieve size to the power 0.45. So essentially, the horizontal axis for each particular sieve size, you take to the power 45, and then that's how we plot it. Why would that be? Superpave guys, sharp researchers came up with, well, this is how we are going to plot to the power 0.45. So one of the reasons is at the 0.45, the horizontal axis, if you draw a line from 0% to the 100%, a straight line, that becomes your maximum density line. That's the maximum densely packed condition for any gradation for that. So that is one of the reasons. But that, so when you plot gradations, you should be plotting on this 0.45 power chart. So if you do that, then the gradations will look like this. If you don't do that, it will look a little bit different, a little bit weirder. It will look like this. So it will be different. So this is a 0.45 chart. So what you are seeing is the blend number 1. Let's say this is the blend. This is not stockpile. This is the blend. Let's say this is aggregate blend number 1. So this blend, this is the blend this is the gradation of the aggregates inside that mixture. Now, so essentially, the first number, if you look at this, the first sieve to retain more than 10% aggregates is here. The second important property, we don't use this much, but this is an important property. Nominal maximum aggregate size and mass is, in this particular graph, it's 12.5 millimeters. What you are seeing is, so if you look at the gradation, the data between 90 and 100%, the data point between 90 and 100% in practical terms is nominal maximum aggregate size. That's the size, that's maximum aggregate size essentially in the mix. So this particular mixture is a 12.5 millimeter mixture. Which mixture is that in MDOT? 5E, 4E, 3E, 2E?
4E.
4E, yes, it's a 4E mix. We're going to talk about all that, but 4E mix are 12.5 millimeter mix, 5E are 9.5 millimeter maximum size, 3E is 19, 2E is 25 millimeter mixes in that mix design. And this is called maximum aggregate size, that the size that corresponds to 100%. We don't use that either. So we can see the line that connect from 0 to this 100%. This is called maximum density line. Maximum density line. That's the densest condition that you can get. Why don't we design mixes such that all the gradations are around maximum density line? That's the densest packed condition.
No place for the binder.
No place for a binder. So we want place for the binder. If we don't have enough binder there, then we are going to have problems. There's we can't put enough binder to have fatigue properties improved for rotting. Okay, so if you look at an MDOT mix Superpave specification, section 501 of the spec book. So this is the table. If you look at this table, Superpave aggregate blend gradation requirements. So 5E mixes, 4E mixes, 3E mixes, 2E mixes. These are the gradation limits. You can see 5E mix between 90 and 100 is 3/8 of an inch, which is 12.5 millimeter, 9.5 millimeters. This is a 9.5 millimeter mix. This is a 12.5 millimeter mix. This is a 19 millimeter mix, and this is 25 millimeter mix. And we have for low volume Superpave, this is actually it's usually a 12.5 millimeter mix, and we have different ranges for the VSP. So restricted zone, there is a range of zones that are restricted. It's in still MDOT spec. Has that changed yet or not? This restricted zone has been eliminated or not? Last time I checked, it was not eliminated.
Still in 2012.
Still in the 2012 spec? Okay. Nationally that's being removed slowly. The reason why there is a restricted zone is that if you look at this, the gradations, let's say we are looking at a 5E mix, one of the surface mixes, smaller nominal maximum 5E mix. So 9.5 millimeter mix. This is the maximum density line. So restricted zone is a zone that is in this here. In the past research showed that if your gradation is passing through the restricted zone, your aggregates, your mixture is prone to tenderness issues. We may not be able to compact it properly. So that's why they came up with that restricted zone. And but later on they found other evidence of restricted zone is fine. So they started removing the restricted zone from the specs. So now, yes,
Remote attendees.
I can see 6 people there. 1, 2, 3, 4, 5. Actually 5. Should be one of them. Maybe, I don't know.
Oh no, 2 are under Bill West, I believe.
Oh, okay, maybe.
Okay.
By the way, are you saying those sieve sizes on the x-axis there have already been raised to 0.45?
Yes, yes. So they are the number, when you come up with the Excel sheet, you come up with a column of numbers that is to the power that, and then in plotting this is a headache because you have to actually put a text there. The Excel is not going to plot it for you.
Is the text, that hasn't been raised to 0.45, has it?
No, not the text.
Just the
Just the axis, yeah.
the axis itself, but it's still labeled
Labeled the same as, yes, you're right. So the labeled still as 0.75, but actual number there is 0.075 to the power 0.45. Because putting 0.075 to the power whatever, they give you a certain number that you can't really relate to. So people usually put actually a text box there, or there's a software that corresponds to. That's it. Right.